Federated learning is a method that allows multiple devices or organizations to train a shared machine learning model without directly sharing their raw data. This is especially important in healthcare, where patient information is highly sensitive and must be protected. However, when it comes to training large language models for tasks like clinical text classification, federated learning faces big challenges. These include high communication costs because models with millions of parameters need to send updates back and forth, and privacy risks, where even aggregated data could potentially leak sensitive information. In this paper, researchers Yu Li and Lihong Zhang introduce a new approach called Selective Attention Federated Learning, or SAFL. The core idea is to make the training process more efficient and private by focusing only on the most important parts of the model. Specifically, SAFL targets transformer-based language models, which are commonly used in natural language processing. These models consist of multiple layers, each with attention mechanisms that help the model focus on relevant parts of the input text. The key innovation in SAFL is using the attention patterns themselves to decide which layers are critical for a given task. Attention patterns show how much each part of the input influences the model's decisions, so by analyzing these, SAFL identifies layers that are most relevant to the clinical text classification job at hand. Instead of updating and transmitting all the model's parameters, SAFL only fine-tunes and shares updates for these attention-critical layers. This dramatically reduces the amount of data that needs to be communicated between devices, making the process faster and less resource-intensive. For example, in healthcare applications like classifying concepts from clinical notes or analyzing discharge summaries from datasets such as I2B2 or Mimic3, models need to handle varied and sensitive data from different hospitals. Traditional federated learning treats all parameters equally, which can lead to inefficiencies and higher privacy risks. SAFL addresses this by dynamically selecting layers based on the task, ensuring that only the necessary parts are adjusted. This not only cuts down communication bandwidth but also enhances resilience to differential privacy techniques. Differential privacy adds noise to data to protect individual privacy, and by updating fewer parameters, SAFL makes it easier to apply this without sacrificing too much accuracy. To understand how this works in practice, let's break it down. In a typical federated learning setup, clients, like hospitals, train the model on their local data and send updates to a central server for aggregation. With SAFL, each client first analyzes the attention scores from the transformers layers during initial training rounds. They then select only those layers where the attention is most influential for the specific classification task. For instance, in classifying medical concepts, certain layers might be better at capturing relationships between symptoms and diagnoses, so those get prioritized. This selective approach offers three main benefits. First, it reduces communication overhead significantly. The paper reports that by transmitting only selected layer updates, the bandwidth required can be lowered by a substantial amount, potentially up to 50 to 70% in their experiments, depending on the model size. Second, it improves privacy. Fewer parameters are shared and updated, which means less opportunity for adversaries to infer sensitive information from the model changes. This aligns well with healthcare regulations that demand strong privacy guarantees. Third, SAFL can actually improve model performance by focusing computational resources on the most task-relevant layers, leading to better accuracy on heterogeneous data distributions common in healthcare settings. The researchers evaluated SAFL on two key benchmarks: the I2B2 clinical concept extraction dataset, which involves identifying medical concepts like diseases and treatments from clinical notes, and the Mimic3 dataset, which includes real-world discharge summaries from intensive care units. In these tests, SAFL was compared to standard federated learning methods and even centralized models that have access to all data. The results showed that SAFL achieved performance levels very close to those of centralized models, with only a slight drop in accuracy, while greatly outperforming traditional Florida in terms of efficiency and privacy metrics. For context, the paper reviews related work in the field. Parameter-efficient methods like LoRa and Adapter-FL have tried to reduce the number of parameters updated in federated learning, but they use fixed subsets that don't adapt to specific tasks. Privacy-focused approaches, such as DP-Fed AVG, add differential privacy but often lead to big drops in accuracy. Other dynamic methods, like Fed-PEP-TAO and Fed-mask, select parameters adaptively, but they don't leverage attention mechanisms like SAFL does. Additionally, some studies have used attention in federated learning for things like client selection or feature highlighting, but SAFL is unique in using attention to guide layer selection for fine-tuning. In their experiments, the team implemented SAFL on transformer models and measured metrics like communication rounds needed, total data transferred, and classification accuracy. For the I2B2 dataset, SAFL maintained over 90% of the centralized model's F1 score while reducing communication by about 60%. On Mimic 3, it showed similar gains, with improved robustness to data heterogeneity across different clients. This means SAFL could be particularly useful in real-world scenarios where hospitals have varying amounts of data and computational power. One interesting aspect is how SAFL handles the transformer architecture. Transformers stack multiple layers, each with self-attention and feed-forward components. SAFL computes attention scores across layers and sets a threshold to determine which ones to activate for fine-tuning. This process is automated, so it doesn't require manual intervention, making it practical for deployment. The paper also discusses potential extensions, like combining SAFL with other privacy techniques for even stronger protections. Overall, by integrating attention-driven selection into federated learning, SAFL represents a step forward in making large language models viable for healthcare without compromising on privacy or efficiency. This could pave the way for broader adoption of AI in clinical settings, where quick and secure processing of text data is crucial for applications like automated diagnosis support or patient record analysis. The authors emphasize that their method is adaptable, so it could be applied to other domains beyond healthcare, as long as attention-based models are involved.